Alright, welcome to Classical Physics, and we are going to be going over scalars and vectors today. What is a scalar? What is a vector? A scalar is just a quantity with a magnitude. That just means a value. A vector is a quantity with a magnitude and a direction. So let's write some examples down, and that will you'll better understand it after some examples. So scalars, vectors. An example of a scalar could be speed, or time, or energy. These things don't depend on direction, they just have a magnitude, a value. For instance, if you have a car and you're going 50 miles per hour, that's your speed. You're not really going it doesn't matter what direction you're going 50 miles per hour. That's your speed. Time only goes in the positive direction. Energy can't be created or destroyed. You don't have negative energy. And so that's a scalar. It's just a constant number, a value. Now a vector also has a direction with that value. An example would be velocity. Say you're going that 50 miles per hour speed and due northeast. Now you have a direction. So if you have a speed with a direction, then you have a velocity. And of course, if acceleration would be a vector. Since it's a derivation of velocity, of course acceleration would have a vector. You can have a positive and a negative acceleration. You can be speeding up or slowing down or accelerating in one direction or another. So acceleration is a vector. And a very important one for mechanical engineering is force. You not only care about the magnitude of the force, you care about what direction the force is in. So that should kind of explain the difference between scalars and vectors. Scalars are just values. They're just magnitudes, and vectors have that scalar component but also give it in a direction. So that's the difference between a scalar and a vector. Let's look at like a one-dimensional example. So let's say you have this being the x direction. So and this being the y direction, sorry. So let's put this in a different color so you can see. So we have a vector, and it's going, let's say, 6 feet. And if you look at this, we have a scalar component, 6. So this vector has a magnitude of 6 feet in the positive x direction. So we have a magnitude and a direction. That is a vector. If you look, another important component about these vectors, or another important aspect about them, is you can actually add and subtract vectors just like you do anything else in arithmetic, and you will gain a new vector because of it. For example, let's say you have, this is in feet, x direction, y direction. Maybe you go 10 feet, then you go backwards 4 feet. These two vectors can be added together, and one being positive and one being a negative vector. And so that would give you a resultant vector of 6 feet. That is your result. So you can add and subtract vectors to get a resultant vector. And that would make sense. You went 4 feet, 10 feet, and back 4 feet. You went a total of 6 feet in the positive x direction. So now I said the word resultant vector. Let's go into what really is a resultant vector and what are its components, and what are components in the first place. Let's say you have, this is x again, y. Now let's say we have a force, and let's say we have a force, we're going to call it force resultant. So our force resultant is in this particular direction. It's some x value and some y value. So not only do we have a force, but we have a force in a particular direction. For example, like let's say I have a block sitting on the ground, and then there is a force in this direction on the block. So that's what that means. So if you take a look at this force, resultant force, you will not only have the resultant force, it can be divided, I'm going to put this in a different color, it can be divided into its x and y components. Whoops. There we go. So it has a force y component. Well, wow. That's not y. It has a force x component and a force y component. So you can see that a force resultant can be divided into its components individually. So this force, when you put it on a block, this block is feeling a force in the x direction and it's feeling a force in the y direction. Now, why would you think that would even be important? Well, sometimes you have certain areas in an object that could be weaker than other areas, and you want to know what direction forces are applied to this object so that you know maybe your stress focal points. So depending on your angle of your resultant force, you may be getting a lot of stress against this x direction, or you may be getting just a little in this x direction and a lot in the y direction. Depending on the geometry of your object, that may matter to you as far as the stress goes. Also, if you're pushing something along an inclined plane, maybe you want a particular direction to be more emphasized than another. So you'll want to know your stresses or your forces in your x and your y direction. Now, not only will that help you in just an application, but sometimes you don't know this resultant force, but you know its components, maybe based on field measurements or something. Well, just like a triangle here, we have 90-degree angle, and you can actually find this resultant force vector by geometry. As you, I'm hoping, are familiar with the Pythagorean theorem, this would say that fx squared plus fy squared equals f resultant force squared. You rearrange that, and you can get the force resultant is going to equal to the square root of fx squared plus fy squared. So that's very important information. So you can find either your components or your resultant forces based strictly on geometry using vectors. Alright, so now that sounded like a bunch of words that may mean nothing to you right now. So this is what we'll do. Some examples. Alright. Actually, before I even go on to that example, I want to show you, just in the previous example we had a resultant force and we had an x component and a y component, right? Resultant, force x, force y. So we already just saw that key relationship of the force resultant equaling the force x squared plus force y squared, square root of that. That's great, but we also, if you knew the angle of that direction with respect to the x-axis or y-axis, you can use your sine, cosine, tangent relationships to also get those. I wanted to say that, I almost forgot that. So I wanted to tell you that as well. So you could have, for instance, the sine of theta. This is actually very important. Sine of theta will equal the force y over the force resultant, right? And we would rearrange that to say the force resultant, or the hypotenuse, right, times the sine of theta equals force y. So this equation gives us a great way to find our force in y direction if we know the angle and the resultant force. We can get our force y component. Same thing with x, right? Cosine of theta would equal force in the x direction over force in the resultant. Rearranging that, you would get the force in the resultant. There we go, sorry. Force resultant times the cosine of theta would equal force of x. That is a very important relationship. So simple triangle geometry will allow you to get either your force components in the x and y direction or your resultant forces. So you can treat vectors. You can solve these vector components and resultant forces just using geometry. So let's do an example, and we'll find out some new cool things about vectors as we do these examples. So let's say we have an object again. And let's say we have two forces on the object. Let's say we have some force pushing down. Now I'm neglecting the obvious gravity forces, or the obvious normal force and gravity force, anything like that. We're just going to concentrate on the two forces that I'm acting on this thing here. So we have this force, and we'll call it 50 kilonewtons. That sounds great. And then we'll say we'll have this force pushing on this side of the object, 100 kilonewtons. All right. Now, let's say that this force is applied at 30 degrees, and this one is straight down. This is 30 degrees from the x-axis. And we want to know, okay, what is the resultant force here, right? Like, what total force am I seeing, and what direction is that total force happening on the object? Because there should be some total force that looks similar. I'm going to draw the object here. This is what we think should be happening, right? There's this object, and we got those two forces on it. What the object is feeling overall should be some force that's a mix of those two forces, right? Now, the direction and the angle, we don't quite know yet. It could be here. It could be more like this. We don't know that yet. So we have to calculate that to find out, well, what's our total resultant force, and in what direction are they going in? So, before we do that, I want to let you know there's a couple different ways to approach it. And the first principle to know before we get started is a cool little trick that you can do with vectors, and a very cool and a very important principle about vectors. So here is a vector. Doesn't matter, just it's some force in some direction. I could move that vector anywhere in this plane. As long as it is in the same direction and the same magnitude, it is the same vector. So basically, I can move it here, I can move it here. As long as it's the same magnitude in the same direction, it's the same vector. That's very important to remember. Why is that important to remember? Well, let's say you have a vector here, vector here, and you want to add them together. Well, it could be very complicated. Well, I'm not going to say it's very complicated. One way you could do it is you could say, okay, I'm going to divide each of these vectors into its subcomponent. We'll call this vector A and vector B. I could say, okay, we've got a AX or an AY, and we've got an AX. And on this one, we have a BX and a BY. And then we could find those components, right? Let's say we have, this is theta and this is alpha. Okay. So we could say, all right, well, I know that A, that's the value A right here. A is that hypotenuse, that resultant. So I could say, well, I know that A times the sine of theta is going to give me AY. And I know that A times the cosine of theta is going to give me AX. Right? Likewise, B times the sine of alpha is going to give me BY. B times the cosine of alpha is going to give me BX. Right? And then what you could do is say, well, if I add up my AX's, or if I add up all my X's live in Texas, sorry for that, I apologize, that's just terrible. So AX plus BX is going to be, I'm just going to call it R, the resultant in the X direction. And that makes sense, right? All of your combined movement in X direction, no matter what direction. So even if if A was going this way and B was going this way, then the resultant would be the combination of those two, right? It would be this one plus this one, even though if it's a negative direction, just like we saw before in the one-dimensional example. So the resultant, just like we saw in 1D, would be the addition of these two. And that's all we're doing here. AX plus BX is RX. So that gives us our X component of the resultant force. All right. Likewise, AY plus BY is going to give us our RY. That's great news, because now that we have our X and our Y of our resultant force, we could just say our resultant, our total just resultant, our hypotenuse if you want, resultant force would equal the square root of the Rx squared plus the Ry squared, right? So that's one way we could get our resultant, and we could plot it very easily because we know our Rx and our Ry. We go over X and up Y, hit the dot, and then go. So that is a method that you could do to get the resultant force. It is also referred to as the analytical method. The other possibility, sometimes easier, sometimes harder, it all depends on the situation. The other possibility you could get is, let's say we draw our A here. Same thing. This is coming from this same example, right? Draw our A. You can take that B, start from A, and draw B, just like it was going to be drawn. Instead of drawing it here, I'm drawing it here. Now, just like I said before, as long as the magnitude and the direction are the same, it's the same vector. So, what is the advantage of doing something like that? Well, the resultant vector, I'll put it in a different color. The resultant vector, you start from the beginning, go to the end. Now that is your resultant vector. I cannot draw a straight line, so I apologize for that. But that's your resultant vector. So there's resultant. And that was B. So you can do it this way, dividing the components into the x and y, finding out your AY, finding out your AX, BY, BX, and so forth, and get your resulting components, and then take the sum of the square roots. You can do that. You can also do it this way. Put one right in line with the other, and then draw a resultant from the beginning to the end. And then you'll know pretty much right away what direction your resultant is going, right? That'll help you if everything's to scale, right? You'll be able to know exactly where your resultant is kind of headed. So that's also another way, and that's geometrically is how you would do it, is what it would be referred to that way. Sometimes this geometric method is easier. Sometimes it's kind of complicated. I don't know. It depends on how good you are at dividing these out and how many angles are known and being able to do that sort of thing. So let's go back to our example. What was it? 100 kilonewtons at 30, 50 on the vertical. So let's draw it again. Alright, so we've got 50 kilonewtons. And then we've got 100 kilonewtons. And this is 30 degrees from the x-axis. And just for reference, there's our orientation here. Positive. Okay, so let's get started. So let's do the graphical method first. I personally, well, it doesn't really, like I said, depending on the problem, then how you approach it, one way will make more sense to you than the other. All right, so let's just take these vectors and let's just draw them as they are. That way. This would make sense to you because that's what I was saying earlier. You can start from the beginning. It doesn't really matter which one you drew where. You're going to get the same thing. Resultant force looks like that. Right? I am terrible at straight lines. Resultant force looks like that. So let's go ahead and label our stuff here. So we got 100. let's also start putting our stuff down here. This is 30 degrees. Oh, you can't hardly see that, can you? Let's put our 100 here so that we've got some room. 50 here. And we're going to say this is 30 degrees. All right. And that's a straight 90 degree. All right. So, to solve this using geometry, we can't just do like a Pythagorean theorem, right? You have to have in order to do a Pythagorean theorem, you have to have a 90-degree angle. And these are not going to be 90 degrees. For instance, let's put, I actually varied this a little bit from what I had on my notes, so I'll be figuring this out along with you. So this would be 90-degree angle, right? If I went from here to here, that's 90 degrees. So, if that's 90 degrees, that means this is 60 degrees, that whole line there. And you know that if this was 100 and this is 50, one other thing that you might want to note on the side somewhere, I don't know if I'm going to be using it right here or not, just based on what my angles are, but I want to write them down for you so that you can have them in your mind. So there's a law of sines, in case you forgot what they were. So that would be the sine of alpha over A equals sine of beta over B, and equals the sine, let's just call it gamma, over C, which would be the angle, and then the side opposite of the angle. The side opposite of the angle. Law of cosines. C squared equals A squared plus B squared minus 2AB cosine of gamma. And of course, this gamma is the opposite of this C. So angle, opposite side. These lowercase are the links, the sides of the triangle. So any Greek letter that you see is an angle, and then any alphabetic English letter, I don't know the proper way to say that, is a length of a side. Okay, so we've got a 30 degree here. That whole thing will be 60. I'm just going to draw some angles here. If I made this a 90 here, then this is 60 degrees here. Okay, and so if you know this is 60 and this is a straight line, this whole thing would be 180, right? So 180 minus 60 is 120. So now we know this angle here is 120 degrees. So that's really cool. What do we do with that? Well, because we know this length, we know this length, so look at the law of cosines. I know this length, I know this length. I don't know this, I do know this gamma, which would be opposite of the resultant. So, yay! We have everything that we need. So, C squared, in our particular situation, we're going to call it r squared because that's our force resultant. It's going to equal, and we can do either one of these as A or B. It doesn't matter for the equation. So 100 squared plus 50 squared minus 2 times 100 times 50 times the cosine of 120. Okay, and now it's just plug and play, right? We're just going to put our numbers in. 100 squared plus 50 squared. So we got r squared equals 12,500 minus, and we've got cosine of 120 times 50 times 100 times 2, which is negative 5,000, so plus 5,000. And so 5,000 plus 12,500. And then r squared equals 17,500. Square root of that is 132.29 for rounding kilonewtons. So our resultant force between the 100 kilonewtons and the 150 kilonewtons at the particular angles that they're pushing at this object is 132.29 kilonewtons. And because you know that angle there and that side, you also know at what direction it's pushing it at, right? We didn't solve for that, but you can solve for that, like with the law of sines, because now you know the sine of 120 over 132.29 is going to equal, and we'll call this this angle here, let's just call it beta. So we'll say it equals the sine of beta over, let me keep that in green so that equals the sine of beta over 50. And that would be 50 times the sine of 120 equals 132.29 times the sine of beta. So, what would that be? 50 times the sine of 120 is, see if you still see this, 43.30. And that's going to, and that's going to equal to 132.29 sine of beta. And then you divide that by 132.29. And then you get, let's bring this on over here, right? And that will be 0.327 equals the sine of beta. And so the sine inverse of 0.327, let's just write that, is going to equal beta. And so beta is going to equal 19.1 degrees. So if that's 19.1 degrees, we know the whole thing is 60 degrees, and you got 30 degrees here. You can just calculate it off of whichever axis you want, right? The x-axis or the y-axis. For instance, 60 60 minus 19.1 is 40.9, which would mean this is 40.9 degrees from the y-axis. So we know the resultant force and what angle that it's being applied in. Okay, I hope I didn't confuse you, but you can rewind and play back. Actually, it's terrible. I wrote this example problem out, but I used I used a different direction for the force here, and for some reason I just wrote it vertically down. I actually did an example on my notes before this lesson of another force going this direction at 45, but I, for whatever reason, just didn't do that and decided to go vertical down, and so we all just figured it out together. So that's the geometric way of doing it, but like I said, there's also the analytical way, and I want to show you both so that so you know both, and maybe you can do one way or the other. And so we'll draw that same example, right? We've got the 100 at the 30 degrees, and for whatever reason I decided to do this, 50 kilonewtons going straight down. Alright, so to do it using the XY components, well, obviously the force, I'm going to call this A and B for this particular example. So obviously the force of B in the X direction equals 0. So that does make things simple for us, because this is a vertical down force. So there's no force in the X direction. It's only in Y direction, which also makes it very, very easy for us. Maybe that's why my mind wanted to do this. In the Y direction, it is the entire 50 kilonewtons. So that's force B in the Y direction. Now let's draw our 100 kilonewtons. And I'm going to draw X and Y this way. You could have just as easily, it's completely up to your preference, drawn it this way. It doesn't matter. Like I said, same direction and magnitude, same vector. Okay, so I already know this is 30 degrees. There's my 90. And so to find my force in Y, I'll do this in blue since I'm already up here. And this is referring to little a here. So the force of A in the X direction is going to equal 100 kilonewtons times, what did I say, X direction, and cosine of theta, which is 30, right? So cosine of 30. The force of A in the Y direction is going to be 100 times the sine of theta, of 30. So force of A of X is equal to cosine of 30 86.6 kilonewtons. Force of A in the y direction is going to be 50 kilonewtons. Cool. So now, just like before, we said a force in the resultant x direction is going to equal 0 plus 86.6, which obviously equals 86.6 kilonewtons. Our force resultant in the y direction is going to equal AY, or AY plus BY, so 50 kilonewtons plus 50 kilonewtons. Force resultant in the y direction equals 100 kilonewtons. Yep. And the force total is going to equal the square root of 86.6 squared plus 100 squared. And the force resultant, which thankfully does not surprise us, to be 132.28. I'm going to round to 3. You could kilonewtons. Right? So now we have our x and our y component of force resultant, and there's the force resultant. I will show you what that one was, 132.29. We got 132.3. So good. And we've got the x and the y components themselves, so you can get an angle off of that if you want, but you can basically just use your x and then your y and plot it that way. So, 2 ways to get your force resultant and the components in the directions that they're being applied. So basically that object is getting a resultant force of 132.3 kilonewtons with those two combined forces, and in the x direction it's feeling 86.6 kilonewtons, and in the y direction it's feeling 100 kilonewtons down. So that is vectors in a nutshell. Now of course this way was very fast, much faster, right? But sometimes geometrical the geometric method makes more sense. It really just depends on the stuff that you're looking at and the specific problem. So there you go. So there is vectors and scalars, and I hope that you learned a lot, because this is a very important aspect of physics. Later on you'll learn that it's a very important aspect in calculus, and a very important aspect in engineering, especially as it relates to mechanical engineering. So thank you, and until next time.